Hi, I should start by thanking Katerina for inviting me to this PHI workshop. I'm going to talk to you about three issues that are relevant for data taking and equipment of X-ray for electron spectroscopy. I'm Alberto Herrera from CINVESTAV-Queretaro at Mexico. So this is the contents of the talk. These are three different topics. The first one is about the angular aperture for acquisition of angular XPS data. The second is about the magic angle, the photoelectric magic angle. And the third is about how to integrate data during data acquisition. So, what's the relevance of a spectrometer angular aperture while acquiring angle resolve data? So this is what we mean by angular dependence of peak intensity. It is a high quality set of data, angular data, for a sample which the purpose is to get the profile of the sample. You can see that the data was acquired at different angles from 25 to 75 degrees from the surface. And you can see that the intensity of, for example, this peak has a strong dependence on the angle. So what we do, we analyze the data, peak fit, and then assess the area of each one of these peaks, and then plot this area that we call peak intensity as a function of angle. This dependence, angular dependence, from here is where we get the profile of the elements at the top surface layer. So what I'm going to point out here is that the angular dependence, the experimental angular dependence of each one of the peaks is mostly linear, regardless of the depth profile. It's a bulk peak, and it's a surface peak, but never, in any case, the dependence is close to linear. The lines here are the modeling of the data under certain parameters that I will describe a little bit how we model the data. So this is the data for oxygen 1s, and experimental data is these squares, and it is the line here, the black line here, is the modeling using for the spectrometer the experimental angular aperture of 16 degrees. So we opened the spectrometer to the maximum angular acceptance, and we are able to reproduce very well the data. What if we model the data with only 1 degree aperture? You can see that we get about the same. However, the actual modeling is this one, and this other red line is this one multiplied by a number. So you basically get the same curve, but with much lower counts. So it's a question that how we model the data, how we can reproduce the angular dependence of the peak intensity. We do this by taking into account all the geometrical factors affecting the angular dependence of the peak intensity. This red area here is the overlapping between the spectrometer and analyzing volume, the X-ray beam, and the surface of the sample. We do numerical integration in the region where the sample surface overlaps with these two volumes. Everything is described in this paper. This is a software that we use. It's called XPS geometry. And you can see that all the geometrical factors that define in these shapes are input in this software, so we can reproduce the data. It's a numerical integration. In this case, I'm using a 40 by 40 grid. So the conclusion for here is that you can open the aperture, you get about the same line, about the same angular dependence, but you get many more counts. So now, why there is so little dependence on the angular aperture? You see that for 16 degrees and for 1 degree is about the same angular dependence. Why is that? When you suppose that you get, this is the nominal angle that you are here, and you get the peak intensity of this value. But now assume that you open the angular aperture to include counts for this angle and for this angle. And then if you average these two values here, they average to this point. So you're just adding counts here. If you open even more your spectrometer to get data for this angle and for this angle, they add and they average to this value. So by opening the angular aperture, you're just getting more counts, giving you the same value. The mathematical way to see that is that when you make a convolution of a straight line with any symmetric curve, what you get is exactly the same line. So you can use Mathematica. Here I'm convolving this line, B plus AX, with a Gaussian. And when you do this convolution, what you get is exactly the same line. So in the case of parallel spectrometer, when you get different angles without tilting the samples, you know that there are some problems there in which you cannot get, it is very difficult to get good data at grazing angles. And this is a well-known problem, but also it is very typical that with this spectrometer, a lot of angles are reported. Here is every 3 degrees. This is this measurement. So there's too many angles here. You don't get more information by giving more angles here. So what they need actually to do is to average maybe every 3 points to get a much better data. For example, this oscillation here is not real. It's due to actual to noise. These oscillations are not real. And by the way, this is normalized data. We don't normalize data. So the conclusion for this section is that even if it is counterintuitive, you won't lose resolution when you open. You won't lose angular resolution when you open the angular acceptance of the spectrometer. You only get more counts. You get better data. Okay, next topic. The photoelectric magic angle. Okay, when we do experiments, we shine X-rays to the samples and collect the electrons with a spectrometer. The photons shining by this source have, of course, an electric field that are perpendicular to the photon direction. And for this kind of unpolarized samples, the electric vector can lie in any point here. So what we are interested here is for a given photon is what the angle between the photon electric field and the direction in which the electron escapes toward the spectrometer, the direction. This angle we call gamma, and the cross section, which quantifies, is important for quantifying composition. The differential cross section has to do with the total cross section, with the asymmetric factor, and also with the angle gamma in this way. When you assume that all those polarizations are equally likely, then when it's like averaging this gamma over all possible polarization directions, and what you get is this expression. Now here you have alpha, which is the angle between the spectrometer and the X-ray source, and you not longer have the gamma here. So this is after averaging. So the magic angle is by making this term equal to 0, so it's such that the differential cross section won't depend on the asymmetric factor. So if you make this 0, to make this 0, you have to choose your angle alpha as 54.7 degrees. That's why so many spectrometers with this kind of sources, the angle here is 54.7 degrees. This is called the magic angle. In a monochromatized X-ray source, the history is different. Here you have a source that hits, in most cases, a quartz crystal, monocrystal, that directs the X-rays focus the X-ray into the sample. So in this case, we have two important polarization directions. One is called the sigma polarization, this one, that comes from atoms, from photons in the sigma polarization here. In sigma polarization is in which the electric field is just perpendicular to this plane. That means it is parallel to the monochromator crystal, to the quartz crystal. The other polarization is called pi, is the perpendicular one. So pi prime here is perpendicular to sigma. So there are two different types of polarizations defined by the crystal here. and one is the pi sigma polarization, and one is the pi polarization. So it happens that it is less likely for this crystal to reflect a pi polarization photon than a sigma polarization photon. In fact, the probability of reflecting a pi polarization photon is cosine square of the Bragg angle times the probability of reflecting a sigma polarization. So the reflected beam is partially polarized when it arrives into the sample. When you calculate the cross-section with this partially polarized beam, what you get is a differential cross-section that now depends on the Bragg angle. Now, if you want to find an angle alpha, here alpha, that in such a way that this differential cross-section won't depend on the asymmetric factor, you need to get an alpha, this angle, equal to a value of 58.7. It's not longer 54.7. So all this is described in this paper that was published 10 years ago. So there are some issues with parallel spectrometers because in those spectrometers, the polarization is changing with takeoff angle. So that has to be taken into account to calculate composition. So you will get different compositions at different angles if you don't get that into account. So it is not only important for regular spectrometers, but also important for parallel spectrometers. So the conclusion for this section is that the X-ray Bragg reflection at the monochromator causes partial polarization of the reflected beam. So the beam arriving at the surface is partially polarized. This partial polarization affects the photoelectric cross-section. So you have to take that into account if you want to calculate composition. And the magic angle is now 58.7. Okay, next topic, coherent data integration. So what do I mean by equipment-related instabilities? When we bought the equipment, the monochromator in 2009, we found that when we turn on the spectrometer and on the X-ray beam, we have a change in time. This is time in minutes. We're talking about a few hours here. So we took the 4F, gold 4F data as a function of time, and we saw that the peak of this peak change with time. So this is a problem with the spectrometer because this is not a chemical shift. A problem with the monochromator. It was shifting the energy. Also, the intensity increased and then remains constant. So that was a little bit misbehaving equipment, but that's not only happens in new equipment. We now wait at least 2 hours for the equipment to stabilize after turning it on. But anyway, there are changes. There are shifts due to the equipment. So if you take data, for example, at 35 degrees, and then at 45 and 55, and then if you have a shift in time, what you get is that apparently the peak is shifting. But when you, okay, this apparent shift with angle might lead you to think that you have two peaks. But when you overlap them, you see that they are just the same. So this is definitely due to shifts of the X-ray monochromator. This is not real shift. It is an artifact of the equipment. So how do you fix that? You fix that by doing coherent data integration. What do I mean by that? Suppose that you have already taken n scans of having 4F and take another scan. So you can see that they are not aligned. So there's a misalignment. What you can do is just align them and then add them. So you can, in this way, you won't widen your peak. You get a better resolution peak. This is the software that we used for doing this alignment. So this is an example without doing the alignment and doing the alignment. So this is an important fact. It might be important. So you can discriminate equipment-related shifts and sample-related shifts. In this case, it is an equipment-related shift because both hafnium and silicon just get the same shift. So you can blame here the equipment and probably the monochromator. But you can also have sample-related shifts. You can have charge centers that shift one peak from another, and here the shifts are different for the different core levels. So everything is here. It is no longer it is still not a paper, just an internal report. You are welcome to download this. Okay. The conclusion is that misalignment and peak widening can be solved with coherent data integration. As a general conclusion, is that if you really take good care of the details, so they are not details, you can get extremely good data, even with a very, very old equipment, 14 years old equipment. You can do that. By the way, this is our software analysis, data analysis software, and this is our main stronghold, that data analysis. Okay, thank you very much. I forgot to say that this is the people in the group that makes everything possible. I should, these are the most important people in the laboratory.